Today's lesson will begin Unit 5, An Introduction to Functions. We're going to be covering Lessons 1 and Lessons 2. There's vocabulary that I want you to focus on, and I want you to practice with describing graphing in situations, writing incomplete sentences, and what function notation means. Material is found in the student workbook, pages 5 through 10, and also pages 15 through 20. So if you're absent or you miss a day, you can keep up in the I Can. You can find the I Can in our course in Canvas. And also the summary for each lesson is on pages 10 and 20. You're responsible for highlighting the vocabulary and reading through the summary to get familiar as we build on each lesson. In lessons 1 and 2, the learning targets are making sense of descriptions and graphs of functions and explaining what they tell us about certain situations, explaining when a relationship between two quantities is a function and when it isn't a function, and identifying independent and dependent variables. So let's write these down right now. We're going to be going between words we already know and swapping those out. For example, independent is going to be your X variable and dependent is going to be your Y. We're also going to talk about domain and range. So if any of these words that we're interchanging or not familiar with, is as familiar as they should be, write them down and then reinforce them as we move through this unit. It's going to go pretty quickly, so vocabulary is the key. And then use complete sentences to explain function notation in terms of the problem that we're looking at or the situation. Also, understand what function notation is and why we have it. And then use function notation to express functions that have specific, again, we're using the words input and output. We can interchange with X and Y, also domain and range. So don't let that confuse you. Our activities are going to start on page 5. We're going to do a bridge and a warm-up, which we typically do as soon as we get to class. You're doing that on your own, maybe checking homework, answering quick questions, and moving into the next lesson. So always try to come as prepared as you can be and try not to get behind. It will help you, especially this last quarter. All right, we're starting with the bridge. So let me read that, and then I'm going to ask you to fill in the chart that's on page 5. Turn to page 5. Mai's helping her band collect money to fund a field trip. The band decides to sell boxes of chocolate bars. Each bar sells for $1.50, and each box contains 20 bars. Below we have a partial table of monies collected for different numbers of boxes sold. So A asks us to complete the table. So if you look at this first row, we have 1 in the first column for boxes sold and M in the second column for money collected. So you should be able to reason out that 30 divided by 1 is 30. In other words, if you multiply the number of boxes sold by 30, if I'm looking at this pattern correctly, I should be able to figure out each additional row. So if one box is $30, how much would 2 boxes be? How much would 3 boxes be? And so forth. You have another example in this fourth row. Is 4 times 30, let's check our hypothesis, is 4 times 30 120? All right, so it looks like this is the rule. Go ahead and complete this chart by multiplying the number of boxes by $30 to get your total. If you look at the last row, we're going in reverse. So what is the reverse of multiply by 30? Instead of multiplying, we should be dividing by 30. 1,530 divided by 30 should give you what your X value is here. Now I'm interchanging these intentionally, not to confuse you, okay, but we need to learn that our input or our first column is going to be our X value, and our output or our Y is going to be the second column. So if I use X, Y, input, output, B or M, okay, in your mind, start learning that I'm saying the same thing. All right, so let's complete the table, pause the video, come back, and let's see if we match up. All right, coming back, 2 times 30 is 60, 3 times 30 is 90, 4 times 30, we already checked that, is 120, 5 times 30 is 150, 8 times 30 is 240, and 20 times 30 is 600. Practice using Desmos or your graphing calculator to do the math. The more you have that calculator in your hand, the better prepared you are for your end of course exam or any of the tests that we take in this class. Also, we need to get as familiar as we can with the graphing calculator before moving up into any of our math courses. What did you get when you divided 1,530 by 30? Did you get 51? Now we're going to use what we're doing here, our rule in our table. Tables help us organize information. Now we're going to write that equation. So we're going to start with our output. Okay, our output, we could write it as y. Now I'm going to write it as y equal, remember our slope-intercept form, mx plus b. Now b is our intercept. Okay, that's what 0 is. When we sell 0 boxes, we have 0 money. So we're really going to have no intercept. That's going to be 0, in other words. It's going to start right at the origin. Okay, what are we multiplying? What is the rate of change? What are we multiplying each number by? Okay, if our x is 1, we multiplied by 30. So our rate of change is 30. So y equals 30x plus 0. We're not even going to write that 0. But we didn't use x and y. We used m. Now m is our output, so don't get those confused. That's that second column. That's our y. Our input is our boxes sold, or our x. So organize it into a table, and you should be able to write that equation. M equals 30 times B. Now, I really want you to look at this closely because we've been using M as the slope. Now we're using it as a variable. So organize your information, highlight what you need, be able to talk about what each of the variables mean. All right, so which is the independent variable? Independent is going to be our x, and our x is the number of boxes sold. Our dependent variable is the amount of money that we collect. Again, organizing information, looking at it slowly, taking your time to practice. All right, let's do the warm-up on page 6. A customer at a bagel shop is buying 13 bagels. The shopkeeper says that will be $16.25. Now, is the shopkeeper correct? Well, let's look at the menu. If one bagel cost $1.25, is 13 times $1.25 equal $16.25. Use your calculator to check. Okay, that is correct. So the shopkeeper says $13.25. But Jada looks at it. She's there with her friends, and she said, shouldn't it be $13.25? But Priya says, I think it should be $13, and Han says, no, $11.25. Now, all three are correct, just depending on how they're looking at it. Explain how the shopkeeper, Jada, and Priya, and Han could all be right. We've already talked about what the shopkeeper did. He wanted to make the most amount of money, so he simply said 13 times $1.25. But Jada noticed that we could buy 6 bagels for $6. If we buy them in bulk, that's going to be cheaper. Essentially, $6 divided by 6 is 1, so each bagel would cost $1 instead of $1.25. Okay, but she needs 2 of those batches, so she'd multiply $6 times 2, and then she'd add one more bagel, $1.25, and then she got $13.25. Okay, that's cheaper by $3 than what the shopkeeper wants to charge you. All right, now how did Priya get $13? Well, what Priya did is she said, I can do better than that. I can get 9 bagels. That would only cost me $8. Okay, and then I need 4 more for 13. So 4 times $1.25 would be another $2.50. Add that to $8 plus $2.50 would be 8. Who am I looking at? Priya. I'm sorry, $8 plus $1.25. Oh, I need to do 8. Let me look at that. Slow down. Okay, 9 bagels, 10, 11, 12, 13 plus 4 more. So $8 plus $5, 9, 10, 11, 12, 13. All right, so that's what Priya did. But Han said, I can do better than that. I think it should be $11.25. So what Han did is he said, I can get 12 bagels for $10 and add another bagel for $1.25 for $11.25. So Han actually is looking at the menu, getting the best price. So let's turn to page 6 and let's think about what we're looking at in this menu to get the best price for the number of bagels that we're buying. All right, so for 1 bagel, it's going to cost us $1.25. So for 2 bagels, we multiply by $1.25. 2 times $1.25. 1 times $1.25. So we're multiplying by $1.25 all the way down until we get to 6. Okay, because at 6 bagels cost $6. So we're going to put that right here. All right, let's fill in the chart. Use your calculator. Go slowly, and then come back and check. 3 times $1.25 is $3.75. 4 times $1.25 is 5. 5 times $1.25 is $6.25. And this is what we saw. When we buy 6, we're actually paying less than if we buy 5. Okay, and then 7, we're going to buy 6 and then add on another $1.25. And then for 8, we're going to do the same thing, buy 6 bagels, then add 2 more on for a total of $8.50. For 9 bagels, we already have a discount, a bulk discount for $8. So it's going to drop down and it's actually going to be less than what 8 bagels was. This happens often in bakery shops or different places where you can get something cheaper when you buy more. For 10 bagels, we're going to buy 9 at $8 plus 1 more. 11, 9 for $8, add 2 more. And then 12, we've got a discount of buying in bulk. We get 12 for $10. And then 13, we've got to buy those 12 bagels and then add on 1 more at $1.25 for $11.25. So fill in that chart, and then we're going to move to the next page. This is not, the graphs are not in your book, so I want you to take notes on page 6 or even page 9, wherever you can find some a spot to jot things down. But we're working on the bagel shop warm-up. You have some space on page 6. All right, so let's look at the blue dots. That's the shopkeeper's price. Okay, so you can see that he starts at 1 bagel. It's not reasonable to start at 0 because we're not going to sell anybody 0 of something. So he starts with 1 and he's going to increase $1.25. Again, the rate of change is $1.25 each for each bagel that we buy. Now, we're not going to connect these with a line because we're not going to buy part of a bagel. We're going to buy whole bagels. Okay, so we have dots there, but it is in a linear progression. We could lay a line down on top of it. All right, now the blue dots are the shopkeeper's price. You can see his price is always higher, but the open green circles, that's Jada's reasoning. So from what we just looked at, she starts getting lower in price around 6 bagels. Okay, still going up. And then it goes down at 12 and still a little bit lower at 13 using her reasoning. And then the red squares, that's going to be Priya's price. Okay, so at 9 bagels, she saw that discount, that bulk discount, and then she used that rule. So we kind of overlap here if we're graphing everyone's reasoning and points. It's one way to look at this and organize the information. And then finally, the yellow triangles, that's where Han finds an even one more discount when you buy 12 bagels to get it cheaper. So it looks like his prices are always the same or lower than everyone else's. So we're going to take all 4 and we're going to plot the lowest price for each. So you can see that it goes up and down. Don't worry too much about what this is doing. Just understand how we got from here to here because I'm looking for the lowest price. Okay, it tends to be trending in a linear fashion. Okay, but when we get to certain amounts, for example, 6, 9, and 12, if we buy that many bagels, we can get a discount so it drops down. Let's look at activity number 1 on page 7. We're looking at a dog tied to a stake. He has a 5-foot-long leash to his post outside of the store, and his owner runs into the store to get a snack. So each time the owner returns within minutes, and the dog's movement is described on day 1, day 2, and day 3. So we have 3 different things that are happening 3 different days. So on day 1, the dog walked around the entire time. Doesn't really tell us how he's walking around. He's just walking around randomly. On day 2, the dog walked around for the first minute randomly, and then he laid down after the first minute, after 60 seconds, until his owner returned. On day 3, the dog tried to follow its owner, but was stopped by the leash. Okay? And then it started walking around the post in one direction. So the leash is going to stop him, and then he's going to start walking around the same direction until it just gets closer and closer. His leash is going to bring him closer and closer to that post. And then he's going to stop and stay there. All right, some other important information is each day the dog was 1.5 feet away from the post when the owner left. And each day, 60 seconds after the owner left, the dog was 4 feet from the post. All right, I have this highlighted. Let's just try to graph that first one. Okay, and then I'm going to ask you to choose 2 or 3 and graph it. So let's see what happened on day 1. Just going to sketch it out here. We have our X and our Y axis. All right, when I get in a hurry, it's not real straight. All right, so here's our X and here's our Y. All right, are we going to ever go, and time is going to be on our X, and we are, how many, we're talking about seconds. Are we ever going to be negative on the X-axis? Are we ever going to go to -1 seconds? And the answer is no. So I'm only looking at the positive numbers, 1, 2, 3, 4, 5, and so forth. All right, when we start at 0, where is the dog going to be each day? It's going to be 1.5 feet away. So if this is 1 and this is 2, the y-intercept is 1.5. All right, now let's just look at day 1. The dog is going to start at 1.5 and it's going to walk around randomly, but it can only go 5 feet away. I forgot to highlight this up here. Okay, so no matter where he starts, he can only go up to 5. can't go above 5, can't go below 0, can be at 0, that's how far away he is from the post, and then at 160 seconds, he's just out here somewhere. But one thing I didn't put on here is that at 60 seconds, the dog was 4 feet away. So I'm going to say this is 60, and this should be at 4. Okay, now I didn't do a really good job of that. So let's see what that looks like. Again, each day on day 1, day 2, and day 3, each dog starts at 1.5 feet. That's the y-intercept. Okay, on the first day and the second day and the third day at 60 seconds, the dog is 4 feet away from the post. So we should have this point on each of our graphs. But there's no other explicit information given on this graph for day 1, except that he can't go past 5 feet. So yours could vary if you sketch this one. I want you to stop the video and I want you to graph either day 2 or day 3, or maybe even both. But come back and let's check and see, once you have tried it, if your reasoning matches up with mine. All right, let's look at day 2. Again, we start at 1.5, and then we don't know whether the dog goes up or down, but we do know that at 60 seconds, the dog is at 4 feet. And then the dog lays down on day 2, so that distance stays consistent. It doesn't change. Okay, on day 3, the dog starts at 1.5 feet and then follows his owner rapidly. So the first 2 or 3 seconds, he's going straight up. And then he can't go over 5 feet, so he starts to come back down again because he's wrapping around that post. So he's coming down slowly. At 60 seconds for each day, the dog's going to be 4 feet away, and then he's going to continue to wrap around the post till he gets closer and closer to 0. Is it possible to see how many times the dog changed direction? So think about what you graphed, what you drew, and the answer is no, because your graph should be different than mine. A little bit variation in these in the direction that they moved, except for the last one. We know he's going in the same direction, round and around that pole. But we only have these 2 points where x is 0. We know what y is going to be. All right, go to the summary and glossary. Make sure that you're highlighting and understanding what a function is. We've just started out, but we've talked about independent and dependent variables. Independent variables are going to be your x, also called the domain, and dependent variables are going to be your y's, also called your range. Or another way that we can say this is our input and our output. Okay, but really slow down, get familiar with what that is, look at the examples, and be ready to keep building on this information because it's going to be consistent pretty much in this section and the next section, Unit 5 and Unit 6, even 7 and 8. All right, independent and dependent. Read all of this, highlight it, take notes, and come back if you have any questions. All right, I'm going to go over this with you because we're going to get into this in the next lesson. We always write this sentence starting with y. Y is always going to be our answer. Our answer, our y, or our output, another way to say it, is a function of x, or our input. Let me write those words down. You write them down in your book also. So the output is a function of the input. In other words, whatever we put in for x is going to tell us what our answer is. I forgot the N, input. Another word that we can use for y is range, and for x is domain. So really learn what these words mean and know that we can interchange them. All right, now looking at this, again, time is typically our x-axis. So what does 125, 400 mean? 125 is going to be the time in seconds. So 125 seconds after, what are we graphing? A plane at takeoff? 125 seconds after takeoff, the plane is 400 feet. Let's look at the definition of a function and let's really look at these examples closely. So let's start with the definition. A function is a relation in which every input or x has exactly one output. All right, no x is repeated, so no repeats. And if we have a graph, it also passes the vertical line test. Okay, so let me draw a vertical line, and we're going to use that for our test. Let's just sit here for a second. All right, now let's go back to the bottom left-hand corner, and let's look at our examples. In this first example, we have coordinate pairs. So here's our x. Remember, if we're looking at our definition, we're not going to repeat our x's. Okay, so we have -1, 0, 2, 3, and 4. Do we have a repeat? No. So here's a function with this example, with this set of 1, 2, 3, 4, 5 points. Now let's look at a mapping of these points, -1, 0, 1, 2, and 8. Again, I'm looking at the x, and none of these repeat. Now we can repeat the y's, but the x's cannot be repeated. So this is a function. We check each of our x's. One's a -1, one's a +1. No repeats. Now let's look at a table. Again, we're looking at the numbers. Do we have another -3? Nope. Another 0? No. 3? No. 8? No. -10? No. So no repeats with our x's. And then we go to the graphs. The graphs I like because they're quick and easy to look at. We just take our vertical line, and I'm looking at this linear equation, and I'm going to pass it from left to right or right to left. Does it touch that line ever in more than one place? The answer is no. Now let's look at the wave on the bottom, that green up and down wave. It's either sine or cosine. Again, moving that line from left to right, it does not touch that wave in more than one place. Okay, but now let's go to the bottom right-hand corner and let's show why these 1, 2, 3, 4, 5 examples are not functions. Let's start with the vertical line test first and go to that bottom parabola. And if I move from left to right or right to left, you can see quickly that we have 2 points of intersection. Except for the vertex on the end, it's intersecting that parabola in 2 places. For the circle, same thing. Unless we're on the circumference or the edge of the circle, we're intersecting at 2 points. Okay, so these two are not functions. They are equations of a circle and a parabola, but they are not functions. Functions have a one-to-one relationship. Now let's look at our domain and range if we have a mapping. So we have 1 here, 2 here, 3 here, and 4 here. If I don't look closely and I'm rushing through, I could say I only have 1 one time, 2 one time, 3 one time, and 4 one time. But that's not true because 4 maps to 2 different numbers. So you could actually list 4 again, mapping not just with 7, but with 9. So it maps with 7 and it maps with 9. So we have 4 on here, 2 different places. All right, so this is not a function. This is not a function. This is not a function by the vertical line test. Let's look at our pair of points. -1, 2, 3. I have 3 2 times. So I can quickly see that this is not a function because 3 maps with 8 and with -12. It maps with 2 different numbers. Now finally, let's look at the bottom table, and I can see quickly I have -2 in our x row twice, mapping with 2 different numbers. These are not functions. So practice those, take notes, because those are quick and easy if you have a visual and you understand the definition. All right, complete the cool down in Canvas. Do this on your own. draw a picture. That gives me feedback, and you get credit for doing this, for using the vocabulary, writing in complete sentences, and it tells me whether we need to go back and repeat something or whether maybe you were absent, you missed a lesson, and we just need a little remediation after school tutorial. All right, turn to page 15. Okay, we have a table. So this first row is going to be your X value. Again, I'm going to repeat this. Your X is typically time. So we're using a T for years. And your Y value, the second row, is typically going to be your output. And our output is millions of tons. So what does this table represent? It is the amount of garbage that was produced in the U.S. each year between 2002 and 2010. So we have our years and we're going up 1 year each time. So look carefully, understand what's happening in the table. We're going to start simple, but it will get challenging if you don't have something to build on. So you can see we're going up 1 year each time. Now we're going to call this function G. So G of X, or G of T, that first row is going to be our input, and that's going to be years. Okay, G of T is going to equal to the tons of garbage. I'm just going to put Y. Y is always going to be our answer. So let's just look at the table. How much garbage was produced in 2004? So let's find that year, and you'll find your answer. 249 million tons. In what year did the U.S. produce 251 million tons? So let's find our Y value now, 251 million. So that's year 2006. Now, if you get in a hurry and you don't slow down, you're going to miss 2008 because we also have that same amount in 2008. Now, if the data in the table were graphed, what would the point 2010 to 50 represent? Again, your X is going to be your time in years, and your Y, your output, is going to be millions of tons. Okay? Let's put that into words. In 2010, there were 250 million tons of garbage produced in the United States. Blank is a function of blank. It's always going to be Y is a function of X. Now let's translate that into words. What is your Y value? It's going to be tons of garbage. I'm just going to write garbage, but on your paper, I want you to write tons of garbage. Is a function of years, or you can say time in years. All right, now let's go back to our dog where we graphed how far he was from the pole on day 1, day 2, and day 3. We're going to use these 3 graphs to answer the questions about the 3 days. Part A, how far away was the dog from the post 60 seconds after leaving? So I can look at each of these, and we already talked about this earlier. On day 1, day 2, and day 3, the dog was 4 feet away. So fill that in along with me. Now pause the video and answer B, C, and D, and then come back and we'll compare answers. All right, welcome back. Let's go to B. How far away was the dog from the post when the owner left? So that's our, when X is 0, before we start clocking any time, the dog started out 1.5 feet away on each day. So on day 1, we have 1.5 feet, 2, and also on day 3. All right, after 160 seconds when the owner returned, how far away was the dog from the post at that time? So let's look at day 1, go to 160 seconds, and I'm just going to have to estimate. So here's where your answers can be a little different than mine. Okay, but you know it's between 3 and 4, closer to 4. So on day 1, I put about 3.7 feet. Would you be wrong if you put 3.8? No. Or even 3.9. So just whatever it is that you saw, your perspective. On day 2, we all should have gotten 4 feet because the dog laid down and didn't move. And then on day 3, again, 160. Where do you think that is? Between 0 and 1. I just looked at it quickly and I estimated a half of a foot, or 0.5. Part D, how many seconds passed before the dog reached the farthest point it could reach from the post? So I'm looking at day 1, and we're going to look at the peak. The farthest it can go is 5 feet. Can't go over 5 feet. Okay, and that looks like it's somewhere between 40 and 60. So I said about 50, about halfway between. All right, the peak on day 2 is somewhere between 20 and 40, closer to 40. And I said 34 seconds, just an estimate. On day 3, the dog went quickly to 5 feet, and that was just a few seconds out, so I put 3 seconds. Okay, now you can vary by a few seconds, but you've got to stay within what is reasonable and what's appropriate. All right, consider the statement, the dog was 2 feet away from the post after 80 seconds. Do you agree with that statement? So let's look at 80 seconds. Is the dog 2 feet away here? Nope, a little over 2 feet. Okay, 80 seconds, the dog on day 2 is at 4 feet. And then 80 seconds, the dog is 2 feet away only on day 3. So this is how I would write my answer. I agree with the statement for day 3, but not for days 1 and 2. You could say, no, I don't agree with this statement because it's only true for day 3, but not all 3 days. All right, question number 3. What was the distance of the dog from the post 100 seconds after the owner left? So let's look at 100. On day 1, it's between 2 and 3. On day 2, it's 4 feet. And then day 3 is between 1 and 1.5. Okay. Day 1, about 2.25 feet is what I said. Day 2, 4 feet. And then day 3, about 1.25 feet. And you can vary a little bit. The only one that we need to agree on exactly is on day 2. All right, so let's turn to page 17. Now let's talk about function notation. F is going to name our function, just like any variable, A, B, C, D, E, F, G. Any letter can name our function. And if we have more than one function, we need to be using more than one letter. We typically start with F. So that first letter is the name of your function. What's inside the parentheses is the input of the function. That's what we put into, if we've got an equal sign, into that expression on the right-hand side of the equal sign to do the math and to get an output or an answer. All right, again, input is our X, output is our Y, or our answer when we substitute in our input. All right, let's turn to page 17, and you're going to be doing activity 1, then comparing your answers with me. But we're focusing on what function notation is. So if you look at where we start, we're still talking about day 1, day 2, and day 3, and the example of the dog and the distance from the post. All right, so we're letting day 1, let's highlight this, or we get confused, and I want you to practice highlighting because it's easy if you organize your data. It is confusing if you don't. So F is for day 1. Let me use a different color for each day, and that will make it easier for me to refer back to. All right, I'm going to use pink for day 2, and we're going to use, keeps going back to green. Give me a minute here. All right, so G is going to be day 2, and H is going to be day 3. Okay? All right, so we write the distance from the post 60 seconds after the owner left. Again, remember our X was time. Time is going to be always going to be, I'm going to say most of the time, our x-axis. And our output, or our amount of whatever it is that we're measuring, water, garbage, whatever, is going to be height, is going to be our y-axis. So this time we're talking about the distance from the post 60 seconds after the dog leaves, because our input is going to be our time. Our graphs, we're talking about how far the dog was away from the post in terms of seconds. So how do we write function notation for day 2? Okay, we're using G for day 2, so we're going to use the same notation, but we're just going to replace F with G. That tells us we're looking at day 2. And how do we write function notation for day 3? This time we're using the variable H for day 3. So the way that we read this is with the information given, how far the dog was away 60 seconds after the owner left on day 1. G of 60 is how far the dog was away from the owner after the owner left from the post on day 2. And then day 3, how far the dog was away from the post on day 3 after the owner left. All right, let's move down to the distance from the post when the owner left. Do you remember where we were on the x-axis when the owner left, when we first started timing? We were at 0. So on day 1, we write that as f of 0, day 2, g of 0, and day 3, h of 0. And then finally C, the distance from the post 150 seconds after the owner left. On day 1, we note it this way. On day 2, g of 150, and day 3, h of 150, because that's the way the word problem asks us to define these functions. Now let's name functions that relate the dog's distance from the post and time since the owner left. Again, same thing. We're using F for day 1, G for day 2, and H for day 3. So let me highlight those again. And keep that straight. All right, what is F of 15? Tell me what that means. If I ask you to write that out in words. So you've got to read the word problem. So that means on day 1, 15 seconds after the owner left. That's how far the dog was away. So F of 15 is the distance from the post 15 seconds after the owner left on day 1. Write that down, practice it, and then go on to B and C. And then stop the video, try this on your own, and then come back and let's compare answers. All right, G of 48 is the distance from the post 48 seconds after the owner left on day 2. What does H of T represent? Well, H is going to be day 3. So it's the distance from the post, T seconds, we don't know the exact number, after the owner left on day 3. All right, now we have an equation, G of 120 equal 4. So we have the whole equation. We have function G, so this is talking about day 2, 120 seconds after the owner left, and now we have the output. The dog was 4 feet away. Okay, make sure you understand how we're interpreting this. So using that, what does H of 40 equals 4.6 mean? What does F of T equal 5 mean? What does G of T equal D mean? Stop the video, try this, come back, and let's compare answers. All right, starting off with A, H is the 3rd day. So on day 3, 40 seconds after the owner left, the dog was 4.6 feet away from the post. Practice again for F of T. F is function for day 1. So on day 1, T seconds after the owner left, the dog was 5 feet away from the post. Now we're going to go to G of T. That's day 2. So we read this as on day 2, T seconds after the owner left, the dog was D feet away. D is going to be the amount. The input is always going to be time. Okay, jot that down. If you didn't get it, just go through these examples slowly and don't skip over it, and come back and ask questions. Practice your assignment. The more we practice, the more that we push through, the easier it will become. All right, page 18. We're still talking about function notation. If I have a rule, we don't always have a function or the graph of a function. So let's reason this out. All right, rule B takes a person's name. So they gave you Abraham Lincoln, and his birthday is the output. So the input is X, the output is Y, input is name, and output is birthday. So I'm interchanging these as you will see it interchanged in the lessons and in the questions given to you in practice and on your test. So the more you practice, the more comfortable you'll get with answering the questions. It will get easier and easier. All right, now I want you to think of 3 other people. You can ask your classmates, you can use yourself, you can use your relatives. I just looked up some birthdays, so I found some names: Rosa Parks, Nelson Mandela, and Mother Teresa. Don't use my names, use different names. And then find that person's birthday. That person is not going to have more than one birthday. They're only going to have one birthday. So for every input, you should only have one output. So think about our definition of functions. Is this a function? Yes. For every input, there's only one output. Now let's compare and contrast that with Rule P. Now I'm giving you the birthday, August 26th. I just picked a birthday, and then I looked up a person, or maybe I knew a person whose birthday was August 26th. Now I want you to come up with 3 different dates and then match those dates with a person who has that same birthday. Now let's think about this. Is there only one person that's born on September 26th? No, there are several. There's Serena Williams, but maybe your birthday's on September 26th. Okay, do the same thing for 2 other. This time we're starting with the date and then coming up with the name of a person. Now you can use the people around you, you can use classmates, you can ask them their name, but their name is going to be the output this time. So why would Rule P not be a function? Because for each birthday, there are many people that were born on that same day. Okay, we're not talking about the year, we're just talking about the day. So let's answer these questions on page 18. If you use your name as the input to B, how many outputs are possible? Okay, so if you put your name in, you only have one birthday. Explain. Don't stop at just the answer. Okay, if you put your name in, everybody only has one birthday. If you use your birthday as the input, how many outputs are there? We already said that. There are many possible because there are other people whose birthday is the same. All right, only one of the relationships is a function. That's relationship B. P is not, because it has multiple outputs for each input. For the relationship that's a function, write 2 input-output pairs. So let me show you my example. You have to have filled in your table with something different than mine. I have Rosa Parks for my X, and my output, my Y, in other words, is February 4th. So what pair do you have? I have another pair, Mother Teresa, with August 26th. Okay, jot down your answers, pause the video if you need to, and then we're going to move on. All right, just for fun, on page 19, we're going to look at this a little closer. Slow down. Now we have the function f, and then we have the word 1, not the number 1. Okay, we get an output of 3. And then f of 2, same function, we put in a different word, we get an output also of 3. Okay, for f of 3, we get an output of 5, and f of 4, we get an output of 4. Okay, so what that means is we take the word as the input, and the output is the number of letters. The word one has the letter O, N, and E. Okay. 2 has 3 letters. 3 has 5 letters, not different letters, just letters in total. All right, here's some input-output pairs. Now we're going to use the function v of the word 1, but this time we're getting the answer 2. So what could be the rule for function v, where we're getting the same words we're putting in, but we're getting out different answers? All right, stop if you need to, think about it, and then come back. All right, function v, the input is a number word, and the output is the number of vowels. So we're looking at vowels this time. All right, make sure that you do the cool down for the lesson 2, a growing puppy. So let me just talk you through this before you start it on your own. It needs to be done before leaving class and before you start your practice. All right, function Q gives the puppy's weight in pounds. So again, the amount is going to be the answer to this function when we put it into an expression. The input is going to be the age. Again, input is time in months. Okay, so what does this expression mean? Q of 18 means how much the puppy will weigh in 18 months. All right, look at B. B has the Q, the function, and the time, but it also has the answer or the output. Okay, the way that we say this is that in 30 months, the puppy will weigh 27.5 pounds. All right, question number 2, use function notation to represent each statement. So if I were you, I would put time is your X, so we're talking about months, and output is your Y. Okay, it's the amount of pounds that we have. All right, so let's use function notation. I'll just use F. What is our input? Our input is our X, or our time, is equal to, output is always Y, 19.6. Okay, when the puppy was M months old, so again, time is going to be your X, and weight is going to be your Y. Okay, you can use any letter for your function. I'll use G this time. Whatever X is going to go in as your input. Okay, so this time our X is going to be M for months equals, our output is always our Y. We're not going to put Y, it told us what to use, W for weight. So G of M equals W. Now go slow and it will make sense. And then slowly highlight and read through the summary and the glossary, especially those vocabulary words that are bolded, and then make sure it makes sense. Okay, here I can see we have 2 graphs. Which one is which? They define that for you, so practice with function F and function G. Make sure that you understand what they're saying. Understand function notation. The name of the function is this letter here. The input is going to be in the parentheses, and the output is going to be your answer. All right, practice is on pages 11 through 13, questions 1A, 1B, 2, 3, 4, and 6. Complete these in your workbook first, because if there are any questions, I can always go back to the workbook to get answers. And then pages 21 through 23, 1 through 5, 7, and 10. Again, I'm going to emphasize this because some of you are missing the cool down, an easy grade, because you're not completing the cool downs before you're leaving class. You've got to complete those before leaving class or they are late. Okay, but you have to do them. They will be graded for completion unless you're just ignoring them and not trying at all. Okay, so that's an easy way to get a grade in the grade book, because it is feedback for both you and me to understand something. So get the cool downs done first, and then get the practice problems done in your workbook. You can have those turned in by 11:59, but essentially midnight tonight, before it's counted late, 5 points off for each day late.